Hello everyone, welcome back to the 18th tutorial class on digital communication. Due to my personal commitment, I am not able to take few class in the earlier weeks. However, right now I shall continue the lectures on this digital communication tutorial class as usual. Okay, let's move on. So coming to the content of this class. So first of all, we will study the operation of optimum filter, and then we shall calculate the probability of error, and after that we shall also discuss about the match filter. Okay, so basically all these optimum filter or match filter are one kind of receiver. Okay, so based on their performance we name it as optimum filter or matched filter. In the last class I have discussed about the most simple receiver, that is integrate and dump filter. An integrate dump filter consists of a simple op-amp based integrator circuit. Okay, and in this class we shall discuss about the optimum filter. As the name suggests, optimum, that means the filter or the receiver has maximum advantage. Now what is the maximum advantage of a receiver? That means the probability of error should be minimum. Okay, so the definition of the optimum filter should be look like this, that it is a simple receiver or detector circuit which have the purpose to minimize the probability of error, and that is called the optimum filter. Moreover, here we shall consider a generalized filter that is used to receive binary signal, and let us also consider that the noise is Gaussian in nature. That means the mean of the so mean is 0. Okay. Now coming to the mathematical analysis of the optimum filter. Suppose the transmitted signal is polar energy type of signal. So the input to the receiver can be given by like xt, as the used line coding is polar energetic. So for 1 the transmitted symbol will be plus a, and for 0 transmitted symbol will be minus a volt. Okay, so obviously the input signal xt will be either x1t, that means plus a, or x2t, that is minus a, depending upon the polarity of the signal. Okay, so whenever 1 is transmitted we get the positive polarity, and whenever 0 is transmitted we get the negative polarity. This figure basically show an optimum filter circuit. Here you can see that the received signal xt is added with the noise. So noisy input to the optimum filter is xt plus nt. Now the output of this optimum filter will be either xo1 plus not or xot plus not. So when xt equal to x1t, that means when x1t is transmitted, that means when 1 is transmitted, the output will be x1 xo1t plus not, and when 0 is transmitted, that means when xt equal to x2t or minus a, in that case y2 will be xot plus not. However, if there is no noise, that means in absence of noise the output of the receiver will be yt, the output of the receiver yt is xo1 only. That means there is no noise, that means there is no term associated with the noise. Okay, so yt is x1 if xt equal to x1t, and yt equal to x02t if xt equal to x2t. Simple. However, when the absent noise is present, sorry, when the noise is absent, so there is no problem to take decision. That means decision can be taken clearly. Okay, but when the noise is present, and that is the uh, most convenient, that if the noise is present, then we can select both. That means output can be either x1t or x2t. Basically, remember that our objective is to identify which symbol is transmitted, either x1t or x2t. Okay, it should be the decision should be taken. That means our the objective should not be that to reproduce x1t or x2t, but to take the decision x1t or x2t, which symbol has been transmitted. So when the noise is present, the filter, optimum filter, can select x1t. Sorry, yeah, if yt is closer to x01 than x0t. Okay, consider the line that optimum filter will choose or will take decision that the in received signal is x1t if yt is closer to x01 than x0t. Okay, and when uh, xot when yt when yt closer to the xot than the x01, then the decision will be in favor of x2t. Okay, so that means the decision is depending on the value of both x01 and x02. So therefore there is some kind of decision boundary, and that decision boundary is nothing but the middle point of x01t and x02t. That is, the decision boundary can be written as x01t plus x02t by 2. Okay, so that is the, you can say it as threshold also, or you can call it as the decision boundary. So whenever the output of the optimum filter, that means this value is closer to XO2t, that means it should have been assumed the received signal is x2t. And when the output of the optimum filter yt is closer to the x01t, then the decision will be like this, that the received signal is x1t or received signal is 1. Okay, so depending on this value, the decision must be taken. So here the importance of the x01 and x02 value is very much. Now consider the Gaussian noise. So let us consider the fact that x2t was transmitted. So output should be xo2t, but somehow due to presence of noise, the output of the optimum filter become like this, that xo1t is greater than the xot. So if noise is NO, if noise NOT is positive and larger in magnitude compared to the voltage difference between the decision boundary and minus the xo2t, that means the magnitude is larger compared to the voltage difference between xo1t plus xo2t by 2 minus xo2t, then the incorrect decision will be taken. Okay, that means the output will be closer to the xo1, and uh, the decision will be in favor of xo1t or 1. Okay, that means an error will be introduced. So when the error will be introduced, so for particular in this case, if the noise value of the noise voltage greater than equal to xo1t plus xo2t by 2 minus xo2t. Okay, so by simplifying it, no2 not greater than equal to xo1t minus xo2t by 2. Okay, so similar to the now consider the PDF of the integrated dump filter power density function. So the PDF of the power density function, sorry, PDF of the random function like noise, that is expressed using this function fx equal fx not equal to not equal to 1 by sigma root 2 pi into e to the power minus not whole square by 2 sigma square, where sigma is the standard deviation and this function, this PDF function, have the mean of 0. So this distribution is showing in this figure. Here you can see that in along x-axis we plot the noise not, and along y-axis we plot the function PDF fx not. Okay, so this is the basically random function. So it can be clear. So this is the point x1t minus x0t by 2, and this is the minus x1t minus x0t by xo2t by 2. Okay, so when the value of not greater than equal to xo1t minus xo2t by 2, then the error will be introduced. So how can we get this value? So to evaluate the probability of error, we must integrate the area under PDF curve from not greater than equal to xo1t minus xo2t by 2. So obviously this point is the this point xo1t minus xo2t by 2. So we should integrate from xo1t minus xo2t up to infinite. That means we want to find out the area under this curve. So the probability error is nothing but the probability when the value of noise greater than equal to this value. Okay, and that can be written by using this integration from xo1t minus xo2t by 2 up to infinite fx not into d n not t. So by using similar approach that has been used in the integrated dump filter, and where we have used the complementary error function, the probability of error for an optimum filter is given by pe equal to half erfc xo1t minus xo2t divided by 2 root 2 sigma. It may be noted that ERFC, that is the complementary error function, is monotonically decreasing function. Hence, P is decreased as the difference between x1 and x2 become greater and the RMS value of sigma becomes smaller. Uh, so the optimum filter has to maximize the ratio x1t minus x2t by sigma. In such a manner, the probability of error become minimum. Okay, so coming to the next point, the optimum filter that should minimize the probability of error PE. So to obtain or to minimize the probability of error PE, we need to maximize the ratio, that is xo1t minus xo2t by sigma whole square. So to maximize the ratio, the transfer function that can be reduced, and that can be written by using this equation of hf equal to k into x star f minus divided by s nif into e to the power minus j2 pi ft. Okay, that is the complex conjugate x star f. Okay, and where s nif equal to input spectral density and xf equal to xo1t minus xo2t. Moreover, maximized SNR can be written as by uh, value of xo square t divided by sigma square, that maximum value of it. So that is nothing but uh, xo1 minus xo2 t by sigma whole square, and the maximum value of it, that is the SNR value, and that can be written as like from integration from minus infinite to infinite mod xf whole square uh, by SNIF into DF. Okay, so that is the value of SNR, and that is the value of optimum filter sorry, that is the value of probability of error for the optimum filter. Okay, that is lots of mathematical equation, but the concept is very simple. There is simple or very small difference between integrated dump filter and the match optimum filter. So basically, for the optimum filter, the probability of error is minimum. Now coming to the matched filter. So the match filter is one type of optimum filter, but the noise is assumed to be as white Gaussian noise. Okay. So for white Gaussian noise, we can write that the input spectral density for white Gaussian noise is like NOT by 2. Just if we substitute this value into the earlier equation, we get the ultimate nothing but the matched filter. So first of all, in this class, we want to find out what will be the impulse response for a match filter. So we know the transfer function for an optimum filter can be written by k into extra f by snif into the power minus j2 pi f. Okay, so hf equal to k. If we substitute value of snif as no2 by 2, so we get this equation k into extra f by no2 by t into the power e to the power minus j2 pi ft. So ultimately we can write hf equal to 2k into x star f by no into the power minus j2 pi ft. Fine. And now we know we can we know that x star f for complex conjugate of xf is nothing but x minus f. So you can write hf equal to 2k by n0 x minus e to the power minus e to the power j 2 pi ft. Now by using the property of Fourier transform, we can write that Fourier transform of x minus t equal to x minus f. Okay, so ft equal f Fourier transform of x t minus t equal to, in the frequency domain, it can be written as like x minus a into e to the power minus j 2 pi ft. So by substituting this equation into the earlier equation, we get, and using the inverse Fourier transform theorem, so ht equal to inverse Fourier transform of hf, we can get ift equal to 2k no into x minus f into e to the power minus j 2 pi f capital T. So ht equal to 2k n naught equal into x t minus t, because basically we substitute, so inverse Fourier transform of x minus f e to the power minus j 2 pi f t equal to nothing but x t minus t. So just we substitute this equation into here, and we get ultimately this equation. So this one is the capital X. So we already know the capital X is nothing but the difference between x1 and x2. So ht equal to 2k by no into x1 capital T minus t minus x capital T minus t. So this one is the basically the impulse response for the matched filter. So coming to the conclusion part, so basically in this class we have studied the operation of optimum and matched filter, and basically we have calculated or we have observed the um, PE is minimum for the optimum filter, and in case of match filter we consider the noise is as white noise. So that is the basic difference between optimum and match filter. And in the next class basically we shall calculate the corresponding probability of error for the matched filter, and we can also observe some kind of numerical problem based on the optimum and match filter. And after that we'll study the operation of correlator, which is the most useful receiver that is used in the digital communication system, that consists of a multiplexer and integrator. Okay, so thank you. This one, these are the some references, those are used. If you have any question, please post them. Thank you.